Alright, so here's the last one. It's going over the last three problems, 15, 17, and 19. So, 15. Find the angle theta that maximizes the area of the isosceles triangle with length L. So, if we have our isosceles, length L, and theta. Okay. So, to find the area, if you're given two lengths and the included side, you're going to be using a little formula called 1 over 2 AB sine theta. Okay, this is one of our area formulas that you probably don't remember from pre-calc, but it is something that we have gone over. And since our two sides are the same, they're both L, our area is 1/2 L squared sine theta. Okay. Now, since we don't have those actual numbers, our answer is gonna have L in it. Okay, and L is not our variable. Theta is our variable. So now when we take the derivative of this, we're taking dA over d theta, okay, or the derivative of it. So that means we're going to keep this 1/2 L squared in front. Okay, that's not changing. It's not our variable. It's our constant. Now, what's the derivative of theta, or derivative of sine? That's cosine theta. Okay. So now we want to find, okay, when does this equal 0? Well, when is cosine equal to 0? Remember our bounds, we're going to be between 0 and 180 degrees, which means we go from 0 to pi. Okay. And we're going to keep our answer in radians because this is calculus, and we like using radians. Well, cosine is 0 when the x value is 0 on your unit circle, which occurs at 90 degrees, which is also pi over 2. So that means when theta is pi over 2, that's where we have our critical point. Okay. Now, if you were to check our area with our different points when we plug them in, sine 0 is 0. Sine of pi is also 0. So the other two gets a 0. When we plug in sine of pi over 2, we get 1, which means that our area would be 1/2 L squared times 1, which means the maximum area we can have is whatever the squared legs all over 2. That is our maximum area, and that occurs at pi over 2. So the hardest thing here was just identifying using this formula and remembering, oh, this is where I can use this formula in this problem. Otherwise, the rest of it was pretty straightforward. Also remembering that theta was your variable and not L. L was your constant. Alright, so 17, we have find the area of the largest it's isosceles triangle that is inscribed in a circle with radius r. So by looking at what this image would be, we'd have an isosceles triangle r, r, r. Now, what I'm going to do here is that I'm going to take this and I'm going to blow it up a little bit. And what we have is, with an isosceles triangle, two of our triangles will be exactly the same inside. This one and this one will be the exact same size. Everything, it'll be congruent triangles. Now, what we're going to do here is we're going to be looking at this third one, the one that's not going to be the same, this angle down here. I'm going to divide it in half. I'm going to say this is theta and this is theta. Okay, so I'm dividing this triangle in half. Now, if I were to continue this line, this angle right here would be pi minus theta, okay, or 180 minus whatever that measure is. This one would be exactly the same. Okay. And then this one down here, this whole measure is 2 theta. Okay. So now we've got our theta, which is our changing variable, because as we expand, or as we change the length of the isosceles sides of this triangle, the central angle of the triangle changes as well. So now our area formula, okay, would be 2, which are these two triangles, times 1/2 sine of the angle, pi minus 2, or pi minus theta, and then we're going to add it to the bottom triangle, which will be 1/2 sine 2 theta. Okay. Now, in both of these, I also forgot to mention the lengths of each side. Well, since it's isosceles, all these are equal, and they're all the radius of the circle, we would have it r squared for both of these. Simplified down, we get r squared sine pi minus theta plus 1/2 r squared sine 2 pi. And now we take the derivative because we want to maximize the area. And so, when we take the derivative of the first one, or when we take this derivative, okay, we can change this right here, can just be theta, okay, just because of how sine works out. And so when we take the derivative of this, we get r squared cosine of theta plus r squared cosine 2 theta is equal to 0. Okay. And so that's just how it works out, and that's our derivative. So now what we'll do is that we'll try to find where we zero these out. And so when we identify it, there's two locations. It could be, this zeroes out when theta is equal to pi and pi over 3. Okay. And so what we'll do now is that we plug these into our area formula from here or here, and then we find, okay, where are we going to max or min it? And then we'd also check 0, because that's another that's one of our bounds. Pi and 0 get you the exact same thing. Okay, it's not going to change because the sine of 0 is sine of pi. It's the exact same. So that means our maximum will have to occur at pi over 3, which after we plug it in and solve it through, we end up getting about 3 root 3 all over 4 r squared. Okay, and that's just after we plug it in. Okay. And so that is the largest area possible. So the hardest thing here was just identifying, oh, hey, you know, this is the angles, this is what it is. We've got 3 triangles all put together. Okay, and so that was 17. Alright, so here's the last one. So, there's a poster on your wall. You know, it could be a poster of, I don't know, something you enjoy, like a band or a movie. Like, I have a poster of stuff on my walls, and I'm sure you probably do too. Anyway, so the poster has an area of 6,000 centimeters squared. There's a blank margin around the poster that is 10 centimeters for the width on the top and bottom, and then 6 for the sides. And we want to find the maximum dimensions, or the maximum. We want to find the dimensions that will maximize the printed picture. Okay, because we want the most picture. We don't care about that white stuff around the side. And so to find the area, which would be 6,000, or we're going to say our printed area, so this is the printed area without the borders, is x by y. Okay. Now, if you want to do the whole poster, you'll have to add in the width and the margins around the side, which added to both sides, you would add 20 and you would add 12, okay, because you've got 10 on the top, 10 on the bottom, 6 on the left, 6 on the right. And so you would have x plus 12 times y plus 20 is equal to 6,000. Okay. So this is our constriction that we have, or our constraint. So we've got to solve for one of them. I'm going to solve for the y, because we always solve for the y. And we end up getting y is equal to 6,000 all over x plus 12 minus 20. Now you could put it all under one, you could put it under one common denominator if you want. I'm not going to, because I'm different. Now the area of the printed part is x times y, okay, and we're trying to maximize that. So we're going to take this y that we found and plug it in for that y. So we're going to have x times 6,000 all over x plus 12 minus 20 is equal to a. Distribute the x, 6,000x all over x plus 12 minus 20x. And now what do we do with these to optimize, try to get the largest one we ever wanted? We take the derivative of it, which means that a prime would be the derivative here. We'll have to use the quotient rule, which, you know, everybody is fine with. X plus 12 times the derivative of the top, 6,000, minus the top times the derivative of the bottom. The derivative of the bottom is 1 all over the bottom squared. And we're going to subtract that by the derivative of the second part, this 20x, the derivative of that is 20. Okay. All right, peachy keen. Now, on this top part, we can take out a 6,000. Okay, there's a 6,000 in both parts, so we can take it out, giving us 6,000. I'm only looking at the numerator right now. X plus 12 minus x. That can be simplified to just 12. So our new numerator is 6,000 times 12. I'm not going to multiply it together yet because I want to be able to reduce without using a calculator. So what we have now is that we have 0, we're trying to optimize, is equal to 6,000 times 12 all over x plus 12 squared minus 20. Now, if we want to solve this, we could move this 20 to the other side, giving us a 20 is equal to 6,000 times 12 all over x plus 12 squared. Now we want to get this x by itself, so we're kind of just going to switch these, okay, giving us an x plus 12, that whole thing squared, is equal to 6,000 times 12 all over 20. Reduce, getting us x times 12 squared, or x plus 12 squared, is equal to 300 times 12. To get rid of the squared, what do? We take the square root. This looks like it's going to come up as a nice number, which will be x plus 12 is equal to the square root of 300 times 12, which 300 breaks up into 100, which is a perfect squared, times 3. And 12 breaks up to 3 times 4, which is a perfect squared, which would be 2. This becomes 3, and this becomes 10. So it'd be 3 times 2 times 10, which is 60, plus or minus. Okay, so we got plus or minus 60. And now we would subtract 12, getting us our answers as x is equal to 48 or negative 72. Now I got a quick question for you. Can you have a negative length of something? Can something be a negative 72 centimeters? No, that's ridiculous. If that's true, then we don't know anything about this world. So now what we're going to do is that we're just going to get rid of the 72 because it's useless. It's not an answer. So that means our x has to be 48. Okay? Because obviously the length and width cannot be 0 because then it wouldn't have any area. So it's not going to maximize. So x is going to be 48. So now we got to find what y would be. Remember, y is equal to 6,000 all over 48 plus 12 minus 20. Simplify this down. Gets us 100 minus 20, which means that y must be 80 centimeters. centimeters. Okay. So that means our printed area would be 48 by 80 centimeters. And our original dimensions of our poster would be 48 plus 12, which gets us 60. 80 plus 20 gets us 100. 60 times 100 is 6,000, which agrees with our original statement. Okay. Which agrees with the original poster side. And as you see, it came together as a nice round number. Oh, I love it when math comes together in this way. Math is so much fun. And so, there you go. So I hope this helped. If there's any questions on these, hopefully this will clear up any confusion that you have, because that's what I'm here for.